Hello friends, we are discussing chemical energetics, and in the live lecture in detail everything I have discussed, as well as some summary videos also I have given. So in summary video, first summary video I have given various terms used in chemical energetics, means thermodynamics. So various terms used in thermodynamics. Then I have given various laws, four laws of thermodynamics: zeroth law, first law, second law and third law. And now use of that third law to calculate absolute entropy. So calculation of absolute entropy is the next point. Absolute entropy means, yes, delta S we can calculate, but to calculate S we have required third law of thermodynamics, and below 15 Kelvin we have required Debye T-cube equation. So these two things are there. So first we know that, or we have ds, that is change in entropy. Small change in entropy is dq upon T. So this is your equation number 1. Also we have heat capacity. Heat capacity we have discussed in detail in the live lecture. So heat capacity Cp is equal to dq by dt. So change in heat upon change in temperature. So that is the heat capacity at constant pressure, and therefore if you are taking this dt this side, so dq is equal to, you can write Cp into dt. So take dt this side, if changing party, then it will be multiplied here, and dq is equal to Cp into dt. Or you can write this way, dq is equal to Cp into dt. So this is your equation number 2. Now from equation 2, equation 1 becomes, so here dq is equal to Cp dt, that we have to write. So from equation 2, equation 1 becomes therefore ds is equal to, instead of dq put Cp dt, Cp into dt upon T. So this is equation 3. Now I don't want this derivative, so to remove the derivative we have to take integration. Therefore integration of equation 3. So integration of ds into Cp into 1 upon T dt. This one only we have written this way. For temperature, now here variation of temperature. So temperature is varying from 0 Kelvin to T, and when temperature is 0 Kelvin, so let H0 be the entropy and S T be the entropy at temperature T. So this T for T Kelvin, and this 0 entropy is for 0 Kelvin. But by third law we can note this is equation 4, and by third law H0 is equal to 0, that is entropy at 0 Kelvin is 0. Therefore we can write here 0 to St ds is equal to 0 to T Cp 1 upon T dt. So in this equation we have written this way, and if Cp is constant we can take Cp outside the integration also. So Cp is constant, heat capacity is constant, and that we can take outside the integration. So 0 instead of H0 we have written, Cp constant, that we have taken common outside the integration. So therefore now you can take directly integration, or another way, one more thing is there. So 1 upon T dt means d ln T. So that also we can note there. So here ds Cp and 0 to T. So this 1 upon T dt means d ln T. d ln T means derivative of ln T, and derivative of ln T is what? 1 upon T into dt. So this is we can say equation 5. If we are solving this one, so we can get integration of derivative. So it is integration is 1 upon derivative. So it can be cancelled. Integration of ds is only ds, and integration of d ln T is only ln T. So by taking integration of this equation 5 properly, we are getting, therefore integration of ds is yes, and upper limit is St, lower limit is 0, is equal to Cp into ln of t, upper limit t, lower limit 0. So therefore here upper limit minus lower limit St minus 0, and here Cp ln of t minus ln of 0, and therefore we are getting St is equal to Cp into ln of t. This equation we can say this is equation number 6. Another way also we can write, therefore St is equal to Cp. So instead of ln t means log to the base e. So I want log to the base 10. For that we have to multiply there by 2.303. So 2.303 Cp log t to the base 10. So this is equation number 7. So this is the absolute entropy at temperature T. But this can be calculated above 15 Kelvin. Below 15 Kelvin, it was difficult to find the heat capacity. So Cp cannot be calculated below 15 Kelvin, because below 15 Kelvin means very less temperature, and very less temperature it is very difficult to calculate the heat capacity. So below 15 Kelvin, since it is very difficult, to calculate Cp below 15 Kelvin, equation 7 cannot be used below 15. Below 15 Kelvin equation 7 cannot be used. Then how it will be calculated? So Cp cannot be calculated below 15 Kelvin, and we have written the equation. So this St is equal to, so equation 7 in another way also we can write the same equation 7. So equation 7 other form we write equation 7 other form can be written in integration form. So St is equal to, we can write, instead of equation 7 we can write in terms of ln t also, so no problem. So Cp ln, or that we can write in integration form. So Cp is not constant there. Then what we have to take? We have to write Cp, St is equal to Cp d ln of t, and temperature is 0 to T. So this one is 0 to T, but 0 to 15, this Cp is not constant. We cannot take common Cp. So 0 to 15, 0 to T1 Cp written this way, plus then T1. So T1 is like 15 Kelvin. So 0 to 15 Kelvin. So this Cp we can't take outside the integration. So we can write this way. And then next 15, T1 to T d Cp ln T. So there we can take that common. So d ln this one. So T1 to T we can take Cp common. Below 15 Kelvin it is difficult to take common. Then that problem was solved by Debye rule. So by Debye T-cube rule, below 15 Kelvin Cp can be calculated. So below 15 Kelvin it is very difficult to calculate Cp, but by using Debye T-cube rule we can calculate Cp below 15 Kelvin also, and that Debye T-cube rule is Cp is equal to A T-cube. So Cp, heat capacity, is directly proportional to T-cube, and this is, we can note, this one we can note first, equation 8, and this one is equation 9, where A is constant, proportionality constant, and that depends on system, which system is there. So where A is proportionality constant, where A constant. Now from this equation 9, equation 8 becomes. So we have to write this A T-cube here. So from equation 9, equation 8 becomes, so we can write there, so therefore ST is equal to 0 to T1, so that is 0 to 15 Kelvin. Cp, instead of that we can write the T-cube rule, so A T-cube into d ln of T is equal to not equal to plus, and here we can take the Cp common because constant there, that Cp is constant, and this is T1 to T2 d ln T. But here Cp is not constant, that we have to find by the Debye rule, and therefore this one is used there, and therefore we can write St is equal to, so 0 to T1, but this is A T-cube and d ln T, so that is 1 upon T dt. Also we can write derivative of ln T plus Cp T1 to T2 d ln T, so this one. Therefore St is equal to, now here we can take A is constant, so that A we can take common, and T and this T, one T will be cancelled here, and there will be a 0 to T1. So here T raised to 3, here T raised to 1. So if it is coming on the numerator, it will be minus 1. So T raised to 3 minus 1. So that is T square we can write. So dt plus Cp T1 to T2 d ln T. So here we are taking Cp common. Here directly we can't take, so because till 15 Kelvin Cp cannot be calculated directly, and we have to use Debye T-cube. So therefore St is equal to, now we can use the formula integration of x raised to n. So this is the formula, integration of x raised to n dx is equal to x raised to n plus 1 upon n plus 1. So here integration of t square. So A into integration of t square is 2 raised to plus 1 upon 2 plus 1, and upper limit T1, lower limit 0. So plus Cp T1 to T2 d ln T. Now we'll solve this one, and we are getting, so we have used the formula, this formula, and if we solve this one, so therefore St, absolute entropy at temperature T, is equal to A in bracket T raised to 3, because 2 plus 1 3 upon 3 T1 0 plus Cp T1 to T2 d ln T. This one. But this is now A T-cube again. So we can write this one, therefore St is equal to A, upper limit is T1. So T1 cube upon 3 minus 0 cube upon 3. So it will be only T1 cube. So Cp integration of T1 to T2 d ln T. Now again solving, we are getting, so this will be 0, 0 upon 3, 0. So T1 upon 3, so T1 cube upon 3. So if we are solving this one, so we are getting, so therefore we are studying this calculation of absolute entropy. After solving this equation, we are going ahead, so write all the points, and therefore St is equal to absolute entropy at temperature T is equal to A into T1 cube upon 3 plus Cp integration of T1 to T2 d ln T. After solving, again this one, so St is equal to, so it is what, 1 upon 3, we can write this way, AT1 cube plus Cp into T1 to T2 d ln T. So this way we can write. But according to Debye T-cube rule, AT1 cube is Cp at temperature T. So again we can write, therefore St is equal to 1 by 3 Cp plus Cp T1 to T2 d ln T. So this way we can write. So 1 by 3 Cp. So this is next equation, equation number 10 we can write. So this way St is equal to absolute entropy. But if phase change is there, then some transition temperature also there, and that transition entropy also added for phase change. Transition entropy should be added in the absolute entropy. So therefore equation 10 becomes for phase change. Therefore for phase change, equation 10 becomes T is equal to 1 by 3 Cp plus integration of Cp T1 to T2 d ln T. This one also we can calculate, find, and plus delta H of transition upon temperature of transition. Transition means if solid become liquid, so at that time this will be melting point. Tm is melting point, and at melting point delta Hm, so heat of fusion, so delta Hm you can write. So that way we can write for absolute entropy this formula for phase change. So this one is the formula for phase change, so it is equation number 11. So formula for phase change. Now entropy of heating of gas. Now entropy, absolute entropy of heating of gas. Heating of gas. So if gas is heating, there will be the diffusion of gas. But gas, how gas is formed? From solid to liquid, liquid to gas, and again we are heating the gas. So this way process is there. So heating the gas, then diffusion of gas will be there. So this is increasing entropy, diffusion of gas. So for this process, absolute entropy St is equal to, first we have to take temperature 0 to melting point, that is solid to liquid, and in that case Cp d ln T. So this formula, heat capacity for that there, and plus melting point, solid to liquid, that is fusion. So heat of fusion, change in heat of fusion upon melting point here. So this we have to add, plus then T melting point to T boiling point, Cp into d ln T, plus we have to add in it heat of vaporization delta Hv upon T. So that is entropy of vaporization we have to add here, entropy of fusion we have added, plus T boiling point, again we are heating, so T particular temperature, so T d ln T, d ln T. So this 5 terms we have to add, first, second, third, fourth and fifth. So to calculate absolute entropy of heating gas. We have to add these 5 terms. So remember all the steps to calculate absolute entropy. So first we have to apply the definition of entropy. Second, then heat capacity definition, formula, mathematical definition, and from that definition, ds again you can change by using Cp value. And once you got that one, then derivative term is there. Remove derivative by taking integration. But whatever equation you are getting, that is not applied between 0 to 15 Kelvin, because till 15 Kelvin, below 15 Kelvin, Cp cannot be calculated. Then we have to use a Debye T-cube equation. So that is Cp is equal to A T-cube. By taking that equation, another way you can find out the absolute entropy. So that all the steps they are mentioned. And if transition is there, that means phase change is there, so then transition temperature we have to add. If solid to liquid is there, we have to add the entropy of fusion, so delta HF upon T melting point. If liquid to gas is there, we have to add entropy of vaporization, that is delta HV upon T boiling point. So here we have added, so T boiling point, this one. And if we are heating the gas, again we have to add PV to T, so that is this one next entropy. So this is absolute entropy formula for heating of gas, and previous also we have derived absolute entropy formulas. So you see all the formulae here derived for absolute entropy. Remember all the steps. Thanks to all of you and have a nice day.